So our lecture today is on continuity of functions. So let's start by just asking ourselves intuitively, what does continuity mean? What should continuity mean? So roughly, it should mean something like this. So here's C. To say that f is continuous at C means that if I make a small change to the input of this function, so I change C to x, then correspondingly there's a small change in the output of the function. So I have f of c, and I made a small change to the input here. I'm going to have correspondingly a small change in the output of the function. So what we have here is small change in input yields a small change in the output. So every teeny tiny step you take to get from C to X here, these little purple dashes, those correspond to tiny steps on a path from f of c to f of x. So this picture would be contrasted in the case where you had something that was discontinuous. So the discontinuous picture would look something like you have this. So you're taking tiny steps over here, and then your tiny steps all of a sudden get disrupted. There's one giant step sort of abruptly bringing you to f of x. There's this kind of break in the picture. So this would be sort of the discontinuous picture. Or at least that's kind of roughly the idea, right? So we just have to make a definition out of this intuitive picture. And the key is to focus on the small change in input means small change in output. So what we need to do to make a definition out of it is to quantify these statements about small change. So to make a definition, to make a rigorous definition, we quantify the vague notions about small changes. And so, again, the way to probably think about this is to imagine someone who's skeptical of this claim. So you claim that if you make small changes to this input, so moving C to X by a small amount, you say that only is going to produce small changes in the output. So you have to imagine a skeptic who says, okay, so let's look at the output then. I challenge you to keep the change in the output less than epsilon by suitably restricting the change in the input. So the skeptic is going to say, I bet you can't make your output differ by less than epsilon from f of c by suitably restricting the input around c. So to respond, what you have to say is, well, in fact, by restricting the input to change by a distance of less than delta, so if I restrict my inputs to this small neighborhood around C, then the outputs do indeed differ by less than epsilon. So you kind of get a picture like this function f takes this delta neighborhood around C inside of this epsilon neighborhood here. So this green here, that's like your f of the ball of radius delta around C. Okay, so here's the kind of dialogue that goes into the definition, and which is illustrated in the picture here. The skeptic says, I bet you can't make the output of the function differ from f of c by less than epsilon. And so the skeptic allows a little bit of room around f of c and says, I bet you can't restrict your inputs around c sufficiently to get the outputs within this epsilon distance of f of c, and you have to respond by saying, well, yes, I can. If I keep my inputs x within a small distance delta of c, then the outputs of the function will indeed be within a distance of epsilon of f of c. So after all that, here's the definition that arises from the discussion. If we have a function defined on a domain A in Rm with values in Rn, we say that this is continuous at a point of the domain if for every epsilon greater than 0, so this is your skeptic's challenge, you can respond with a delta greater than 0, such that when you have points in the domain which are within a distance less than delta of c, so you allow for a small change in your input from c to x, as long as that change in input is sufficiently small, less than delta, that will imply a corresponding small change in the output. So the output changes by less than epsilon from f of c to f of x. And as in the last lecture, with the concept of a functional limit, there's an alternate definition which the text calls the topological version. It's really just taking these conditions, these inequalities, and expressing them in terms of open balls. So x in A, and this inequality just says that x's in A intersect the delta ball around C. And then this inequality here is just saying that f of x, so f of any such x satisfying these things, falls inside the ball of radius epsilon around f of c. Okay, so it's a rather straightforward reformulation, and it aligns with the picture that I drew up here. Right? You have so you have this ball of radius epsilon around f of c, and your goal is to find a delta ball small enough around c such that that gets mapped into that epsilon ball around f of c. Okay, so this is just writing out that picture essentially. So I want to make a remark about our definition, and this is related to the subject of the last lecture. So the definition of continuity at C. So continuity at C looks a lot like saying that the limit as x approaches C of f of x is equal to f of C. Right, this looks a lot like if you take f of c, put f of c equal to L, this definition looks a lot like saying that the limit as x approaches c of f of x equals L. And you have a given epsilon, you have a delta response, and you have some inequalities. But there are some important differences. And basically the difference just comes down to whether C is a limit point of A or not. Okay, so notice for continuity here, of course, you need the C in question to actually be in the domain of the function, right? So that's one difference, is that you're always requiring that C is actually in the domain of the function, so you actually have the value of the function at C. For the limit as x approaches C of f of x, you didn't even need C to be in the domain. So for one, C in A is a requirement in the definition of continuity. But not in limit as x approaches C of f of x. But ignoring this, the most significant difference is that C doesn't have to be a limit point. Doesn't have to be a limit point of A in the definition of continuity. Okay, so in this definition of continuity, we're not assuming that C is a limit point of A. So the situation looks like this. So for any A, for set A, A is equal to the limit points of A. So we have limit points of A. And to be clear, I mean limit points of A that are in A. Of course, there can be limit points of A not in A. So there's limit points of A that are in A, and then there are isolated points of A. Okay, so you have these two different kinds of set. So maybe I'll want to denote these by different colors. Okay, and this is a disjoint union. So the sets involved in this union are disjoint. And that's just directly from the definition. An isolated point of A is a point in A that has a little neighborhood around it, such that that point is the only thing in that neighborhood, in that little epsilon ball around A. Whereas if you have a point in A that's a limit point, every epsilon ball around that point contains other points of A in it. Okay, so these are completely sort of opposite notions. So let's look at what continuity means for these different types of points of A. So let's say we have C in this set here. Then saying that f is continuous at C, it's easy to see that that's just equivalent to saying that the limit as x approaches C of f of x equals f of C. Right, it makes sense to talk about the limit as x approaches C because C is a limit point of A. And then it's really easy to see, right, just because it's the same kind of call and response definition for limit point as it is for continuity. You're given an epsilon, you have to respond with a delta, and one inequality implies the other. So the only thing to clarify, I guess, is in the limit point situation, you have a greater than 0 inequality here implying this inequality there, but that turns out to make no difference in this case. And that's just because so allowing for 0, so if you don't have greater than 0, allowing for 0, that just means x equals C. But when x equals C, f of x equals f of C, that's 0, and that's less than epsilon for any epsilon. So that's sort of just a trivial difference there. Okay, so continuity for a limit point of A. So for a point of A that's a limit point of A is just the same thing as the limit concept that we learned last time. But if you have a point C, which is an isolated point here, that's different because it doesn't even make sense to talk about the limit as x approaches C. So the limit as x approaches C in this case, and maybe I should, let's make sure I separate these two. So the limit as x approaches C of f of x is not defined, so it doesn't even make sense. And in fact, the notion of continuity at C is trivial. So in fact, f is trivially continuous at C in this case. And why is that? Well, because by definition of an isolated point, this means there's a delta neighborhood around C such that C is the only point of A in that delta neighborhood, right? Well, if that's the case, then I can use that delta as my response for any epsilon. So given any epsilon whatsoever, I can take that delta as my response, and then the only x in A satisfying the inequality that the distance between x and C is less than delta is C itself, right? So C is the only point in this delta neighborhood that's also in A. And so all we have to check is that the distance between f of C and f of C is less than epsilon. But of course, the distance between f of C and f of C is 0. So that's trivially less than epsilon for any epsilon greater than 0. So that's why the continuity of f follows immediately for such an isolated point. Okay, so sort of the definition of continuity is this limit definition. That's the one given in calculus, but really when this definition is given in calculus, it's assumed that the point C that you're talking about is a limit point of the domain of the function. So the definition, careful definition above that we've given covers both situations in which you have limit points and isolated points. It makes sense in both cases and sort of has a slightly different flavor in each of those cases. Okay, so that's the difference between the definition of continuity and the concept and this statement here, that the limit of f of x is equal to f of c as x approaches c. So this first theorem about continuity is probably not surprising and gives us a very convenient way to discuss continuity and to prove certain theorems. So this is the sequential characterization of continuity. So continuity in terms of sequences. So we have a typical setup, we have a domain, point in the domain, then the following are equivalent. F is continuous at this point in the domain, And then we have the second statement here that if you have a sequence drawn from the domain which approaches that point C, then the sequence of values, right? So you look at the value of the function along that sequence, that has to approach f of C. So that's equivalent to saying that the function is continuous at C. So let's just look at the proof of this. So the basic idea of the proof is going to be to use the fact that if C is a limit point, so if C is a limit point, then continuity, that's equivalent to saying that the limit as x approaches C of f of x equals f of C. And last time we saw that that's equivalent to the statement that if you have a sequence xn in A, but where the sequence never uses the value C. So if you have a sequence converging to C but never equal to C, then f of xn, the f sequence approaches the limit, right? So it approaches f of C. And clearly, this statement here looks pretty similar to this one here, the only difference being the A and the A minus C. So we should be able to make some fairly quick argument that these are equivalent in the case of a limit point. And so then we just have to look at the case where C is an isolated point and make a slightly different argument. So basically just going to try to use some work that we already did in the previous lecture. So we'll first suppose you could also give a direct argument for the equivalence of these two. It would be very much similar to the sequential characterization of functional limits that we did in the last lecture. So first, suppose that C here is an isolated point. Then as we saw above, one is automatically true. But also 2 is automatically true here. But also 2 is automatically true. Since the only sequence xn that can satisfy xn converging to C, or I guess I should say the only sequences that can satisfy xn converging to C are sequences that are eventually constant at C, are eventually constant sequences. Right, this point is isolated, so the only way you can have this sequence getting arbitrarily close to C, the only points in A arbitrarily close to C is the point C itself. So our eventually constant sequences xn equals C for n bigger than or equal to some capital N, for some big N in the natural numbers. So if xn is such a sequence, then f of xn is eventually constant as well. So we have f of xn just equal to f of C when little n is bigger than or equal to big N. So the convergence of that sequence to f of c is automatic. Okay, so 1 and 2 are automatically true statements when c is an isolated point. And so, you know, a true statement implying a true statement is always true. So we have, so 1 and 2 are always true. C is isolated. Thus, 1 and 2 are equivalent. Okay, so now suppose that C is a limit point of A. Then 1 is equivalent to saying that the limit as x approaches c of f of x equals f of c, and that is equivalent to the statement if xn is a sequence in A which never uses c, and xn approaches c, then f of xn approaches f of c. Okay, so take that statement and compare it to 2. We see immediately that 2 has to imply 1 because 2, right, you're considering more general sequences. If so every possible sequence drawn from A with this property satisfies that conclusion. And here we have a particular kind of sequence which is drawn from A and converging to C. So this is just a subset of the possible sequences in 2. Okay, so then clearly 2 implies 1. So we need to argue the reverse. Okay, so we're going to, suppose, so let's see, I guess I should maybe put this, this thing in red here. Okay, so suppose that, and then we need to show that 2 holds. So that means we need to take a sequence in A that converges to C, and we need to show that the function values converge to f of c. So let xn be a sequence in A which converges to C. Well, the sort of natural idea is to take this sequence and divide it into 2 pieces. One where the xn's are in A but not equal to C, and one where all the xn's are equal to C. So there are two subsequences which exhaust the entire sequence. So you have the xnk such that xn sub k is never equal to C, and x sub n sub L, which is equal to C for every L. So since subsequences converge to the same limit, then we have x sub nk, that converges to C, and x sub nk is never equal to C. So f of x sub nk has to converge to f of C by star. And also f of x and L, that converges to f of C just because it's a constant sequence. So what we have, so thus the original, so if we look at the sequence of values f of xn, is a sort of union of two subsequences that converge to the same limit. And I don't want to belabor the point, but it's pretty easy to see from this that that the full sequence f of xn has to converge to f of C as well. So it follows easily that f of xn, the full sequence, converges to f of C. All right, so that will conclude the proof of that theorem. So we have a corollary, a very useful way to use this theorem is to show that functions are discontinuous. So as a corollary, we have a criterion for discontinuity. Continuity criterion. Okay, so first of all, so let f be a function defined on a domain, and C be a point of the domain. If C is isolated, f is always continuous at C. F is automatically continuous at C. But if C is a limit point of A, and there are two sequences, xn and yn drawn from A, such that xn and yn both converge to C, but the f values, so the limit of f of xn is not equal to the limit of f of yn, then f is not continuous at C. So as examples, this follows from the examples at the end of the last lecture. So if we define f of x to be sine of 1 over x, and this is when x is not equal to 0, and then let's say some number a when x equals 0, this is not continuous, at x equals 0 for any a. Okay, because last time we found sequences of x converging to 0 such that the limit of the f values was different. So it doesn't matter what value you plug in here, you can always find those sequences which have limits that don't agree. So that's sort of 1, and then 2, if we look at the indicator function of the rationals, this being, I guess I should give x, this is, recall, equal to 1 if x is in the rationals, but 0 if x is in the complement of the rationals. This is discontinuous everywhere. Okay, so you'll remember from last time, for any real number, so any real number, right, everything's in the domain, so any real number is a limit point of the domain. And we can always find a sequence of rationals approaching that point, so we have a sequence of f values equal to 1 and a sequence of irrationals, so a sequence of f values equal to 0, of points converging to that given real number. And so our function can't be continuous at that point, and that argument works for any number, so it's discontinuous at every value. Another corollary, which is fairly immediate from the sequential characterization of continuity, is the algebraic continuity theorem, just telling us how you can build up additional continuous functions from given continuous functions. So if you have two functions on a common domain, and they're both continuous at a point in that domain, then if you take either one of these functions and you scale by some real number, then that's continuous. The sum of functions of those two functions is going to be continuous, the product is going to be continuous, and the quotient, provided the denominator is not equal to 0 at the point C, they'll all be continuous functions. Okay, so the proof is just immediate. Immediate from the algebraic limit theorem. And sequential characterization. So as an example of the usefulness of this corollary, basically trivial arguments. So trivial arguments show that f of x equal to the constant function 1 and f of x equal to the identity function x are continuous. And if you don't believe me, you can write out the argument. I'll just tell you. So for the first one, so take delta to be anything, for f of x equal 1 and delta equal to epsilon for f of x equal to x. Okay, so if you take those deltas, it's probably a good exercise to just run through the argument that those are continuous based on the definition. There are such simple arguments. I don't know that it's worth going through. It's probably better for you to see it for yourself. So thus any polynomial p of x equal to an x to the n plus a1x plus a0 is continuous. And I guess I should have said are continuous here on R, so on all of R. Shoot. Kind of running out of room here. Excuse me. Okay, so when I guess I'm not going to make the note, but just when I mean continuous, I just mean continuous everywhere. So any polynomial is continuous on all of R. Okay, since any polynomial, right, so, you know, you're just taking, so since 1 is continuous, any constant function is continuous. Take 1 and multiply it by any constant, that's going to be continuous. Any constant times x is going to be continuous. Then the sum of any constant times x and any constant is going to be continuous. And then any such thing multiplied by x, right? So then any constant multiple of x squared is going to be continuous, and any constant multiple of x cubed is going to be continuous, because you can multiply continuous things together and then adding all of those. So you can sort of build up your polynomials inductively by just starting with these two basic ones. Okay, so any polynomial like that is continuous on all of R, and more generally, any rational function p of x over q of x, where p and q are polynomials, is continuous wherever q of x is not equal to 0. Okay, so this theorem immediately gives us a wide variety of continuous functions. So now I want to look at an example where we use the definition of continuity. So I'm going to suppose we have a function defined on some domain in Rm with values in R. Okay, so just real numbers coming out. And let's say that this function is continuous at some value in at some point in the domain C, and also that the function is non-negative. Because what I want to do is look at the square root of this function. So the square root of that function is also continuous at C. Okay, so this will, in particular, imply that the square root of x as a function is continuous on the domain of non-negative real numbers. So the book does that example. I'm just going to do this somewhat more general example. So there's probably another kind of argument you could make here. But I'm just going to go straight from the definition. So you can probably make some kind of sequential argument, but I'm gonna go straight from the definition. So we need to so let epsilon greater than 0 be given, and we have to find a delta response to this. So what we need to do is, well, what we need to do ultimately is control. So we're going to have the square root of f of x minus the square root of f of c. Right? We're trying to say that the output values change by less than epsilon as long as we sufficiently control the difference between x and c. So as long as x and c don't vary so much, then these output values vary by less than epsilon. All right, so that's what we want. And so we have to somehow do some kind of manipulation with this, and the standard thing when you have square roots involved in a sum or difference is to use the conjugation trick. So what we can do is take this and multiply. So we can take this square root f of x minus square root f of c and multiply by square root of f of x plus square root of f of c over. Now just multiplying by 1 in a fancy way. And what that gives us, right, once we have a difference times the corresponding sum, that's just a difference of squares. So this is going to be f of x minus f of c, absolute value, and then divided by just the square root of f of x plus the square root of f of c. I don't need the absolute value in the denominator because each of those quantities is non-negative. And then what I want is to make this less than epsilon here, right? And I can't, and what I have control over, because I know my function f is continuous, right? So I know I can make f of x minus f of c as small as I'd like just by controlling x and c. So I have control over this, right? So I can control this. So what you kind of like is to take this denominator and move it over here, except the problem is you have this x, right? So this is not a constant right now in the denominator to be moved around. But what I can do is just easily just drop that x, that troublesome x part, right? Because what we have is that this denominator here, so this is bigger than or equal to the square root of f of c. So when you do 1 over it, it's going to be just less than that. So we have this is less than or equal to f of x minus f of c over the square root of f of c. And then I can make that less than epsilon by just taking this, by just making this less than epsilon over square root of f of c. So as long as I make x and c close enough so that the absolute value of f of x minus f of c is less than epsilon times this value, then I'll be good to go. There's just one slight complication here, which is that this f of c might be 0. So this expression here might make no sense. And so just separately I'll have to, so this could be 0. So I'll have to handle that case separately. Okay, but the basic thing is, so we need to take care of f of c equals 0 separately. I guess I don't need the square root. So f of c equals 0. We'll need to do that separately, and then in the general case, we'll need to choose our delta. So choose delta such that the difference between f of x and f of c is less than the square root of f of c times epsilon. So first do this case, and then in general. Okay, so that's my scratch work here. So we did this scratch calculation, and then that gives us this summary down at the bottom of how we're going to handle the proof. Okay, so if we let epsilon greater than 0 be given, so first assume that f of c is equal to 0. So in this case, things are easy. The difference between f of x, square root of f of x, and square root of f of c is just the square root of f of x, and we need to make that less than epsilon, but we can do that by just making f of x less than epsilon squared, which we can do because we have control of the difference between f of x and f of c, right? So we can make that less than epsilon squared by just taking x and c close enough. So our epsilon greater than 0 is given. So since f of x is continuous, there is a delta greater than 0 such that when x and c are at a distance less than delta from each other, such that that implies that, excuse me a second, implies that the distance between f of x and f of c, which is just equal to f of x, is less than epsilon squared. So then if the distance between x and c is less than delta, we have that the distance between the square root of f at x and the square root of f at c is equal to just the square root of f at x, and that's less than the square root of epsilon squared, which equals epsilon. So this establishes continuity in this case. So we have continuity in this case. So now assume that f of c is not equal to 0. Okay, so then what we're going to do is just follow our recommendations here. We're going to choose a delta such that this condition holds. Okay, so since f is continuous at c, we can choose delta such that when x and c differ by less than delta, that implies that f of x and f of c differ by less than the square root of f of c times epsilon. Okay, so now that we have that down, we can get rid of our last remnant of scratch work there. So thus, if the difference between x and c is less than delta, we find that the distance between square root of f and, well, square root of f at x and square root of f at c, that's equal to square root of f at x minus square root of f at c times square root of f at x plus square root of f at c. Just repeating our scrap work now. That equals f at x minus f of c, absolute value, over square root of f at x plus square root of f at c. And now this is less than or equal to f of x minus f of c in absolute value over square root of f of c. And that is less than, by our choice of delta, square root of f of c times epsilon over square root of f at c, and that equals epsilon. Okay, so that completes our proof. So same type of game as for showing the limit of a sequence. Right? You're given your epsilon, you just have to kind of look at how you're going to make that thing less than epsilon, try to do some algebra, kind of solve an inequality, and then put all of that scratch work into a nice flowing logical argument. All right, I'll also run through a couple of examples that are in the book, so you don't have to take notes. You can just find the write-up in the text. So another example using the definition of continuity, if we have f of x equal to, we'll take x times sine of 1 over x, where x is not equal to 0. So this is a modification of that crazy function from last lecture and that we saw above a few minutes ago. In this case, we have this x, which is kind of damping this craziness down. So as x goes to 0, this is sort of dragging all those crazy oscillations towards 0. So intuitively, if we define this to be 0 when x equals 0, then this should be continuous. So this function is continuous at 0, is continuous at x equals 0. In fact, it's continuous at any x, but we're not going to argue that here. We'd have to know more about the sine function to do that. So proof, so let epsilon greater than 0 be given. So what we have to do is look at the difference between f of x and f of 0. And this is the difference between x and sine of 1 over x and 0. And of course, that is just x times sine of 1 over x. And what do I have control over? What I have control over is the distance between x and 0. Right? I want to say it's continuous at 0. So if I move away from 0 by a little bit, my f of x doesn't move too far from f of 0. So what I have control over ultimately is the absolute value of x. And so I see that absolute value of x appearing here. And I want to try to make this less than epsilon, of course. And, well, that's, troublesome. I have control over this. Doesn't seem like I have much control over this, except I remember we'll just use the elementary fact, take it as known that the sine function is bounded by 1 in absolute value. So to get rid of all those other x's I don't seemingly have control over, I'll just use the fact that this is less than that. And then I can easily make that less than epsilon, right? So I can make that less than epsilon as long as I take my delta to be equal to epsilon. All right, so I'll write myself a proof then. Just need to take delta equal to epsilon. So take delta equal to epsilon. Then if the distance between x and 0, which is just the absolute value of x, is less than delta, it follows that the distance between, I guess I should be precise, f of x minus f of 0, that's just x sine 1 over x minus 0. That's absolute value x times sine of 1 over x. That's less than or equal to absolute value of x times 1, which is absolute value of x. That's less than delta, and delta is equal to epsilon by definition. Okay, so just showing you how the game is played. As one other example, we can consider the function h of x this is the book's notation. What this means is, so this is equal to n. So I got to say this is equal to n if x is between n and n plus 1. Okay, so we showed where n is an integer. So we showed earlier in the course that that for any real number, you can always put that real number between an integer and a subsequent integer. And so this is the greatest integer less than our real number. So that's the output of the function. And so what that looks like, and if you graph this function, so input output, your function is equal to, it has this kind of step pattern. So let's say 1, 2, 3, -1, -2. Between 0 and 1, it's just 0. But then as soon as you hit 1, it bounces up to 1. So 1, 2, 3. So it's going to bounce up to 1. And bounces up to 2, etc. And it's going to keep stepping down. So what we have sort of clearly is that h of x, from an intuitive standpoint, h of x is discontinuous at every m in z, and continuous elsewhere. So to see that, just let m be in z. To show something's discontinuous, we'll just find two sequences that approach that. You just find two sequences that approach that thing such that the function value sequences along there are different. The limits are different. So we'll consider a sequence, right? So if we take, here's our m. Let's see. So if this is m. Here's our m. We'll take a sequence coming in from the right. That'll have this value here, and from the left, that'll have that value down there. Two different values. So consider x sub k equal to m plus 1 over k. And y sub k equal to m minus 1 over k. So clearly x sub k and y sub k go to m, but x sub k is eventually, not x sub k, f of x sub k is eventually the constant sequence m, whereas f of y sub k is eventually, I guess it's always equal to. So the thing is with the x, the first, right, k equals 1, right, the value of the function is actually m plus 1, and then it drops down to m. But with y of k, the first k, you get m minus 1, and then everything thereafter, you're strictly between m minus 1 and m, and then so the value of the function is m minus 1 always, whereas this is the constant sequence. M minus 1. So it follows, then the discontinuity at m follows. So discontinuity Okay, so now suppose that x is a non-integer point, so x is not in Z. And let epsilon greater than 0 be given. So now what we have is, right, so you're going to have some x like there, and all we have to do, right, so all we have to do, so the output of our x is here on this red part. All we have to do is restrict the variation, or maybe I should use C, since we've been using C before. So we have C not in Z. So let's see, this is C. We just have to restrict our x's near C to be such that, right, they sort of stay in the interior of this interval, so that it lands on this, right, on this flat part. We can't let it stray too much, because then it's gonna jump up to the next thing. And if epsilon is small, if epsilon is less than 1, then that jump of a distance 1 is not going to play well with the epsilon. So since C is not in Z, there is an n in Z such that C is strictly between n and n plus 1. So in our picture, this is n, and this is n plus 1. And then what we want to do is just restrict delta, right, to be like that. So the biggest we can make delta is so that these endpoints here extend out to, whichever one of n and n plus 1 is closer to C. We can let our endpoints extend out that far, but no further. So what we want is, so set delta to be the minimum. Right, so we'll look at the distance between n plus 1 and C, and the distance between C and n. And then we'll take the minimum of those. So then if the distance between x and C is less than delta, we find that, well, what we want to say is that the distance between f of x and f of c is less than epsilon. But of course, we've set things up so that f of x and f of c have the same value, right? So that they're just going to be equal to 0. So what we want to say is just that f of x is between n and n plus 1, so the value of f of x is identical to the value of f of c, that they're both just equal to this n here. So what we'll do is just take this inequality, so x minus c must be less than delta, it's got to be bigger than negative delta, and delta is less than or equal to, well, it's less than or equal to n plus 1 minus c. And also, delta is less than or equal to c minus n, so negative delta is bigger than or equal to negative c minus n. So we have this is bigger than or equal to n minus c. And so what we can do is then add c. So adding c through these inequalities yields n less than x less than n plus 1. Thus, f of x is equal to n, which is the same thing as f of c. So the difference between f of x and f of c is just equal to 0, and that's less than epsilon. Okay, so that establishes continuity at C. And so the final note we'll end on is a general theorem about composition preserving continuity. So let's say we have a function defined on some domain A in Rm going to Rn, and then we want to follow that up by some function g, which is defined on a domain B in Rn going to Rp, say. And since we want to do the composition, right, we want to follow g up after f. Well, then when we do f on A, that better end up in the domain of g, right? So that we can follow f up with g. So we'll assume that f of A is contained in B, and then our composition here makes sense. The theorem says that if f is continuous at the point C in A, and if g is continuous at the image point, okay, so we have continuity at both steps of this composition, then the composition as a function from A to Rp is continuous at the point C. All right, and the proof is actually fairly straightforward. So we want to claim that g composed with f is continuous at C, so we let epsilon greater than 0 be given. So what we want to control is we have g composed with f at x and g composed with f at C. We want to control that, make that less than epsilon, right? Okay, well, so this is g of f of x minus g of f of C. And what we know is one thing we know is that g is continuous at f of C, right? So that means that as long as f of x is close to f of C, that the outputs of those, right? So these f of x and f of c are inputs to g. As long as those inputs are close together, the outputs under g should be close together. So we should be able to make the outputs of g differ by less than epsilon as long as we can make the inputs f of x and f of c close enough together. So by the continuity of g, so continuity of g at f of c, continuity of g at f of c means that as long as there's going to be some delta, so that as long as y and f of c differ by less than delta, that should imply that g of y and g of f of c differ by less than epsilon. So in order to use this, what we need is for the f of x, to fill the role of this y here. So what we need is for our f of x to differ from f of c by less than delta. Right, so we need this y, we need to sort of plug in, right, so this f of x here needs to go in for this y here. Right, so in other words, we need f of x to differ from f of c by less than delta. But we can do that, right, because f is continuous at c, so we have continuity of f at c. So that's going to mean as long as we take x close enough to c, and let's say they're less than some eta, right? There's an eta such that when x and c are less than eta apart from each other, then indeed f of x and f of c are less than delta. And once f of x and f of c are less than delta from each other, that's going to imply by the continuity of g that the g of f of x and g of f of c are less than epsilon away from each other. So basically we just have to, from this given epsilon, there's a d delta coming from g, and corresponding to that delta, you think of that delta as kind of the epsilon in the f continuity, and you derive an eta from that delta. Okay, so that's how the proof goes. So by continuity of g at f of c, there is a delta greater than 0 such that when y is in B and the distance between y and f of c is less than delta, that implies that g of y and g of f of c differ by less than epsilon. Then by the continuity of f at c, there is an eta greater than 0 such that when x is in A and x differs from C by less than eta, that implies that f of x and f of c differ by less than delta. So therefore, if x and c differ by less than eta, then f of x is in B and f of x and f of c differ by less than delta, right? So your f of x fills the role of y from above. So f of x is one of the y above, and it follows that g of f of x and g of f of c differ by less than epsilon. And so that's it. It's really just if you're given epsilon, you have a straightforward delta response, and then to that delta, you also have a further response. So one response coming from the continuity of G, and the second from the continuity of F. All right, so that's going to conclude the basic lectures on continuity and limits for the week.